Okay, welcome to lesson 6 of the transformations unit, the sixth and final lesson. What we're going to be learning about today are dilations. Dilations are the first of the transformations that we're going to learn about that are not isometric. And so all of the transformations we've dealt with so far, translations, rotations, and reflections, are all isometric or congruence mappings. And what we're dealing with today is a dilation which involves either expanding or contracting a shape. And so what we're going to do in this particular case, or what we have in this particular case, is something called a similarity mapping as opposed to a congruence mapping. So if we were to transform using a dilation, a triangle, for instance, the image of that triangle under the dilation would be a similar triangle. So the angles are unchanged and the sides, the corresponding angles are congruent and the corresponding sides would be proportional. When we dilate something, what we need to know are two things. First of all, where is the center of dilation? And the second thing we need to know is what the scale factor is. So in this particular case, this is a dilation centered at 0 or O, the origin, and it has a scale factor of K. One final thing with the scale factor that we need to be aware of: if the scale factor is larger than 1, then we are talking about an expansion. So if the K value is larger than 1, if it is between 0 and 1, then we are talking about a contraction. So we're shrinking the figure. We can also have scale factors which are negative, and what you need to understand with negative, just like a negative on a number line, is that it involves a change of direction. And so when a scale factor is negative, we go in the opposite direction. Okay, and so let me show you what I mean by that. So we're going to come down to example number 1. We've been asked to find the image of triangle ABC under the dilation centered at O with a scale factor of 2. Okay, and so this is effectively what we need to do. So I'm going to get my ruler. I'm going to put it on the center of dilation, and I'm going to measure the distance from O to A. Here you can see that it is 7 centimeters, and what I'm going to do is go twice as far away from O. And so this is an expansion because the scale factor is larger than 1. It's a scale factor of 2, and so effectively what that's telling you to do is for each of ABC's vertices, go twice as far away from O as the original. And so effectively what I've drawn in here is the line that is going to double the distance from O to A, and then A to what will now become A prime. I'm going to repeat that process for points C and B. Okay, and so what you can see now is I've repeated the same process for point C, measuring the distance from O to C, and then using the same length from C to C prime. Same process for point B, and then the final step would be to join, and I'm going to use the line tool over here. I'm going to join the images. So what I have now is triangle A prime, B prime, C prime. You'll see that it is twice as far from O, the center of dilation, as triangle ABC. Okay, so that's the essence of what we're doing. If we come down to example number 2, what we've got to realize now is we have once again been asked to do a dilation, but this time we've been asked to find the pre-image. Remember, when we're finding the pre-image, we're going backwards, we're reversing it. And so essentially what we have here is triangle R prime, S prime, T prime has been created by a dilation about centered at O with a scale factor of 2. if we want to know where the original triangle was, what we're going to do is reverse that process. And so I'm going to get my ruler again. This time what I'm going to be doing is measuring once again from the center to the image. And so we're going from 0 to let's say 6.4. There'll be a little bit of leeway for accuracy here. So 0 to 6.4 is the distance to get to the image. I want to go half as far. And so I'm going to measure 3.1 and make a mark at 3.1. Let's hope that's marked. There we go. So I'm going to make a mark at 3.1, and that will be where the original point was, point R. I'm going to repeat that process for the other 2 points. Okay, and so what you can see is I've done the same thing. I've joined O to S prime. I've marked off the midpoint because I'm going back to the original. I'm reversing the dilation. I've got my 3 pre-images, and now all that remains to be done is to join those 3 pre-images in order to complete my triangle. And so the original triangle, there we go, original triangle RST, which when dilated produced R prime, S prime, T prime. Okay, moving along, we have got a key concept, again, not a theorem, but a key concept, and so this won't be on your theorem sheet. And really what the key concept is doing is extending the idea of what we've just done to apply within a coordinate plane. And it gives us a simple rule that says if you want to dilate, so in this particular case, if I had a dilation of point M centered at the origin with a scale factor of 2, if we've got M's coordinates, we can simply go twice as far if we're doing distance. Similarly, if we're going from O to P, P's coordinates are 2, 3. If we go twice as far, what you will see algebraically is that the coordinates of P are doubled, and this gives you a shortcut or an alternate way to deal with dilations that occur within the coordinate plane. Okay, so let's move down to the next example. So here we have example 3. We've got triangle ABC. We've been asked to dilate it with the center of dilation at the origin, and there's 2 things to pay attention to. First of all, we have a negative, which means we're going to move in the opposite direction. And then the second thing we have is a scale factor less than 1. And so what we're talking about in this particular case is a shrink or a contraction of the pre-image or the original triangle ABC. Okay, so I'm going to go ahead and do that. Again, using the above theorem, you can do that by coordinates if you wish. And so let me show you the coordinate way. I've got the coordinates for C, which are 0, 4. I've got the coordinates for B, 1, 2, 3, 4, and 2 down. So I'm going 4 left and 2 down. And the coordinates for A, 2 left and 4 down. What I can do is use the algebraic rule to find the coordinates of the image, and then I can just plot those on the graph. Okay, so I'm going to do that now. I'll just pause so that I don't run out of time. Okay, so what I've done while you were away, very briefly, is I'm going to use the key concept, the algebra method in this particular case. I've got the coordinates of points A, B, and C. I've literally just taken point A and I've multiplied each of its coordinates by -1/2. So -2 times -1/2 gives you +1, which is where I got this value from. -4 times -1/2 gives you +2, which is where I got the y coordinate for A prime. I've done the same thing for the 3 images, and now all I need to do is plot those points and join them. Okay, so I'm going to go ahead and do that right now. Okay, and so what you can see is that we've now got the image of triangle ABC. It's significantly smaller, and you'll also notice that it appears to have been flipped around. And so I just want to clarify that very quickly, and that is because of the negative. So I want to show you the effect of the negative. If I go here and mark off, or not mark off, but I align my ruler on point A, and assuming I've done this properly and accurately, what we should see is the following, that the distance from the center of rotation to A, which is right about 5 centimeters, you should find the image in the opposite direction. And so that's what the effect of the minus is, that the dilation occurs in the opposite direction instead of in the same direction from O to A. It goes in the opposite direction but along the same line, and then it should be half of the distance because our scale factor was, of course, 1/2. Okay, so the next one I'm going to do by drawing instead of by using the coordinates, and we'll use the same basic approach. So what we've been asked to do in this particular case is find the image of A prime, B prime, C prime. So this is the same as a composition, and so now I'm going to take the dilated figure, and I'm going to dilate it about the origin with a scale factor of -4, and so I'm going to do that, and then I'll come back and explain what I've done. Okay, so what you can see is I've now gone, taken the image of ABC, I've measured the distance from A prime to the center, and I've gone 4 times as far the opposite direction. I've done the same for B prime and the same for C prime, and I've ended up with triangle B double prime, A double prime, C double prime. Okay, last couple of questions. I now need to find the scale factor. If I were to dilate from triangle ABC to A double prime, B double prime, C double prime, what you should hopefully be able to see is the quickest and easiest way to do that is to just take the 2 dilation factors, which are -1/2 and -4, and if we multiply those two together, we get +4/2, which is of course 2. That is the scale factor. So remember, in a composition of transformations like this one, instead of performing the first transformation and then the second, if we were to multiply the 2 dilation factors, since we have the same center of dilation, we can arrive at the scale factor for the dilation that covers the composition of those 2. Okay, sorry, 2 more to go. Okay, so now what I've been asked to do is to find the image of point B, and notice the key here is that we have changed the center of dilation in this particular case. So now A, the original point A, is my center of dilation. I'm going to go twice as far as the distance from A to B, and then figure out the new coordinates for B. And so I'm just going to do this by hand this time in the interest of time. You can see I'm going diagonally across. I'm going to go another 2 blocks on, which is going to be twice as far from A in the direction of B. Not very well drawn. And then I'm going to figure out those coordinates. 1, 2, 3, 4, 5, 6. So we're at the point -6, 0. And that is the image of B under the dilation with A at the center with a scale factor of 2. Okay, last question. If we've got the dilation centered at O with a scale factor of -3, that maps R to R prime. We've been asked to find the length of OR prime. A couple of different ways that we can do this. One way would be just to find the length of OR and then double it, or we can find the coordinates of R prime and then find the length of OR prime. Okay, so just to wrap this up, what you can see, what I've done is I have multiplied the coordinates of R, each of them by -3, the scale factor, which has given me the coordinates -6, -18, which are the image of R prime's coordinates. You can see I've plotted it on a coordinate plane over here. And then if we're asked to find the length of OR prime, basically what I'm going to do is use the fact that to get to point R prime, I've gone 6 units to the left and 18 units down. And so what I can do is use Pythagoras' theorem. So let me just undo that. OR prime is going to be the square root of 18 squared plus 6 squared, which I think will give us the square root of 360. Okay, and so that approximates as 18.97.